Hi, everyone. Welcome and good evening. My name is Benjamin Quinn, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm excited to introduce this virtual event with Nicole Yunger Halpern, presenting her book, Quantum Steampunk, The Physics of Yesterday's Tomorrow, in conversation with Jacob Barandes. I hope you're all well and safe. Thank you so much for joining us virtually. Tonight's event is the latest installment in our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. Coming up in the series on Monday, April 4th, we'll host celebrated neuroscientist Stephen Fleming for his new book, Know Thyself, The Science of Self-Awareness. To learn more about this and our other upcoming virtual events, you can visit harvard.com and sign up for our email newsletter, or check out the page harvard.com/science for more info. I'll also be posting a link to our Science Research Public Lectures channel in the chat, where you can view previous talks you might have missed. This evening's discussion will conclude with some time for your questions. If you have a question for our authors at any time during the talk tonight, click the Q&A button at the bottom of the screen and we'll get through as many as time allows. In the chat, I'll be posting a link to purchase Quantum Steampunk on harvard.com. Your purchases and financial contributions make events like tonight's possible and help to ensure the future of a landmark independent bookstore. Thank you to our partners at Harvard University, and thank you all for showing up and tuning in support of authors, publishers, indie bookselling, and especially for science. And finally, as you have no doubt experienced in virtual gatherings, technical issues may arise. If they do, we'll do our best to resolve them as quickly as possible. Thank you so much for your patience and understanding. Now it's my pleasure to introduce tonight's speakers. Nicole Yunger Halpern is a theoretical physicist at the Joint Center for Quantum Information and Computer Science at the University of Maryland. Her work, which re-envisions 19th century thermodynamics for the 21st century, has won many awards, including the International Ilya Prigogine Prize for her energy science thesis, and as well as the International Quantum Technology Emerging Research Award from the British Institute of Physics. She earned her PhD from Caltech and was previously an ITAMP postdoctoral fellow at Harvard. Tonight, Nicole is joined in conversation by Jacob Barandes, lecturer and co-director of graduate studies in physics at Harvard University, where he is also faculty affiliate of the Harvard Black Hole Initiative. With research publications spanning the foundations of quantum theory, the philosophy of science, and quantum field theory, Dr. Barandes also organizes an international workshop series on physics, philosophy, and their intersections. This evening, Nicole and Jacob have joined us for a discussion of Nicole's book, Quantum Steampunk, a detailed and whimsical dive into the emergent science of quantum thermodynamics, which the always wonderful Sean Carroll calls complex, entangled, and unpredictable. Yunger Halpern provides an expert tour of the bustling new research frontier at the intersection of physics, information, and technology, complete with goggles and brass fittings. Named in part after the fantastical genre that pairs futuristic technologies with Victorian sensibilities, Quantum Steampunk similarly blends the old with the new, envisioning the scientific underpinnings of the Industrial Revolution through the lens of today's roaring quantum information revolution. Beautifully written and brilliantly researched, the book wonderfully explores the field's aesthetics, shares its whimsy, and gazes into the potential of a quantum future. We've got a lot to learn this evening, so without further ado, I am delighted to turn things over to our speakers. The digital podium is all yours, Nicole and Jacob.
Thanks so much for the lovely introduction. Let me share my screen. It's really a delight to be here. So thanks so much to the Harvard Bookstore and Harvard University for having me. When I was a postdoc, I definitely enjoyed the opportunity to participate in the science series as a listener, and now I'm really thrilled to be able to participate as an author. So, since this is a Cambridge audience, then I know it's a sophisticated group, so I can be a little technical. So I'm going to begin with a technical term, steampunk. So steampunk is a genre of literature, art, and film. Steampunk stories take place during the Victorian era, when the Industrial Revolution is humming and London is full of smog and Sherlock Holmesian mysteries. The railroads are cutting across the American West for the first time, and people wear waistcoats and petticoats. Against this backdrop are futuristic technologies, automata, time machines, submarines, and flying ships. The Canadian poet Douglas Featherling has said, "Steampunk is a genre that imagines how different the past might have been had the future come earlier." You might have encountered The Time Machine, this novel by H.G. Wells. It's one of the first steampunk works, as it was written during the 1800s. But steampunk is very much with us still. For instance, The Invention of Hugo Cabret was a New York Times bestseller early in the 2000s. Enola Holmes was one of the first films released on Netflix because of the pandemic. So it's about Sherlock Holmes's little sister, Enola. The film was a hit. I loved it. The sequel is coming out soon. The Nevers is a show on HBO about Victorian women who have supernatural gifts. These works reach back to the past and reach ahead to the future. This fusion of old and new creates a wonderful sense of nostalgia and adventure and romance and exploration. So fans dress up in steampunk costumes full of top hats and goggles and gears and gather at steampunk conventions. So what they dream, I have the immense privilege of having the opportunity to live. I'm a theoretical physicist, and I work at this intersection of three fields: quantum physics, information science, and energy science. In information science, we study how efficiently we can perform information processing tasks. These include solving computational problems, such as calculating a satellite's trajectory, communicating information, such as over Zoom, securing information with cryptography, and storing information in memories. Quantum physics is the study of the very small, such as just a few electrons or atoms. They behave in counterintuitive ways that familiar objects can't. For instance, you might have heard of entanglement. Entanglement is a relationship that quantum particles can share and everyday particles can't, but produces very strong correlations. So very loosely speaking, in a cartoon sort of a picture, if two atoms are entangled, then if you measure one, then you instantaneously change the other, even if one atom is with you in Cambridge and the other atom is with me in Washington, DC. Scientists and engineers are now leveraging entanglement and other quantum phenomena to build quantum technologies that process information in ways impossible for just everyday technologies. For instance, quantum computers will be able to solve in minutes certain problems that even supercomputers will take years to solve. For instance, fertilizer is extremely important across the globe. In some countries, food security is at crisis levels. In other countries, food security is at the highest levels ever in human history. We invest a lot of energy, about 3% of the entire world's energy output, in fertilizer production. Why do we use so much energy? Because we produce fertilizer using an old technique from 1909. Bacteria can accomplish the same goal much more efficiently. But those bacteria use a molecule, nitrogenase, that's too complicated for us to simulate on classical computers. But that molecule is quantum. So a quantum computer is naturally better suited to unlocking the molecule's secrets and hopefully transforming fertilizer production and energy use. It's little wonder that governments all across the world are pouring money into quantum technologies, education, and research. In 2018, Congress passed the National Quantum Initiative Act, which provided $1.2 billion for quantum technologies. Even more astoundingly, the Senate passed the act unanimously. So everyone in the Senate actually agreed on it. The quantum companies are booming. At least 3 quantum startups have spun off from Harvard: Lero, Quantum Diamond Technologies Incorporated, and Zapata. Now, this object belongs to IBM. This is not a quantum computer, although it does look cool enough to be one. It actually looks steampunk. This object holds a quantum computer, which fits on a small chip. The chip needs to be at low temperatures to support quantum behaviors such as entanglement. So this device cools the quantum computer to temperatures lower than the temperature of outer space. This device is a dilution refrigerator, or to those of us in the field, a fridge. Actually, when I told my husband that, he was indignant. He said, this cools things down to below the temperature of outer space, and you can't even call it a freezer. Anyway, cooling leads us to the third element in our triumvirate, thermodynamics. Thermodynamics is the study of energy. It was developed during the Victorian era, since engines were powering the Industrial Revolution and powering factories for the first time. People wanted to know how efficiently these engines could operate, so they developed the theory of thermodynamics with a practical bent. However, these practical questions led to fundamental questions, such as why time flows in only one direction. Now, cooling, expelling energy, is a thermodynamic task, but how do you measure the heat emitted by a quantum system that's cooling down? To measure the heat emitted by an everyday object, you could measure a system's energy, cool the system, and measure the energy again. Then the initial energy minus the final energy is the heat lost. But quantum systems are more delicate than everyday systems. Probably a number of people here have heard of Heisenberg's uncertainty principle. Werner Heisenberg helped found quantum theory during the 1920s. He intuited that if you measure a quantum system, you inevitably disturb it. So if you measure a quantum system's energy, then you change the system's energy. So how we can measure quantum heat or even conceive of quantum heat isn't straightforward. Furthermore, this fridge here is a large system of many, many atoms. What if we tried to build a fridge from a quantum system? Could we? How small could we make it? Could quantum phenomena such as entanglement benefit the quantum fridge as they benefit quantum computers? More generally, just as there are information processing tasks, such as encrypting information or communicating information, there are thermodynamic tasks, such as refrigerating and powering cars and charging batteries. Given that quantum phenomena benefit information processing tasks, can they also benefit thermodynamic tasks? How can we extend the Victorian theory of thermodynamics from large everyday type systems, such as steam engines, to small quantum and information processing systems? These questions underpin quantum thermodynamics, the field in which I work. My colleagues and I re-envisioned the thermodynamics of the 1800s for the 21st century. So we reach back to the past and head to the future. The resulting fusion of old and new I call quantum steampunk. So a genre of science fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. Looking forward to talking with Jacob next.
Thank you. That was wonderful. So hello, Dr. Yunger Halpern. I'm really glad to have this opportunity to ask you questions about your wonderful new book, which I very much enjoyed reading. I highly recommend it. There's a lot to talk about, so if it's all right, let's get started. I'm going to start in a maybe somewhat unexpected place. You argue in your book that aesthetics used to play a broader role in science. In what sense did you mean that? And why do you think it's important to incorporate aesthetics into science going forward?
I'll start off by saying that aesthetics are in physics today in that we recognize that simple equations that describe very diverse systems are regarded as elegant. And there's, in some cases, an attempt to unify, to slim down theories to their basic ingredients, because that too is regarded as elegant. On the other hand, during the 1800s, even the physical instruments used in science were beautiful. They were made of wood and brass, and they had extra decoration that they didn't, strictly speaking, need to have. But they appeared to be not just tools, not just instruments, but really works of art. And if you fast forward by about a century and look at the tools of the 1960s, you'll see big, chunky gray objects. Some of the tools that we use, I think, have turned back into works of art. For instance, there's a quantum computing company based near where I am in Maryland, IonQ. They have a box that basically contains their entire setup. And it has very clean lines, it's simple, black. And so it was designed to look neat and sleek, let's say. So aesthetics might be returning to the scientific instruments we use, even though they look a bit different than the brass and wood of the 1800s. Why is it important to me to have aesthetics in my science in this way? It reminds me of the saying, you are what you eat. In a sense, you are what you use day in and day out. And I would like for our work as scientists to be beautiful. I think there's something poetic about using instruments that are beautiful as well.
That's really great. So you incorporate a lot about your personal story in the book, including your path to becoming a scientist. You talk about how a painting by Robert Van Branken inspired you, and even about your own entanglement ceremony. That's really a wonderful aspect of your book, especially for students considering a career in science who might not find it difficult to visualize how, what the trajectory is of a person who goes into science. Particularly, you write that you started off in the philosophy department in college. How did you end up moving toward physics, and why did you choose to incorporate so many aspects of your personal story into this book?
There are many reasons why I ended up in physics. I've always loved studying everything. So I actually really didn't want to commit to any one major. I just wanted to keep studying all the disciplines I possibly could. I've always had a philosophical bent. I've always been attracted to abstract ideas. I've always loved reading, and so building universes in my head. So I loved physics and math, but I did want to keep studying everything. So I went to the philosophy department because a philosophy teacher in high school had imbued in me his curiosity about quantum physics and special relativity. And the philosophy department had some professors who were willing to work with me, but I didn't quite find what I was looking for. And I ended up finding it in the physics department, where there are some really excellent physicists who had done really foundational, wonderful research, but they were very open to looking at physics from many different points of view. So they helped me put together a major that's about halfway between the physics major and the create your own major. So I chose a number of physics courses and a few math, history, and philosophy courses related to physics. So I got to view physics from many different angles. And by the time I finished doing that in college, I determined that it really was physics that I wanted to focus on and study very deeply, which is why I went to grad school. Actually, so right after I signed up for my major with the physics department, I found this painting that you mentioned by Robert Van Branken that's discussed in the book. So I was interning in Washington, D.C. at the Smithsonian Institution Libraries. The Smithsonian, people usually think of as having museums, but it has a wonderful library system, including the Dibner Library for the rare books and special collections pertaining to the history of science. It's an amazing collection. It has second editions of Galileo's works and manuscripts handwritten by Einstein and so on, and some aesthetically quite beautiful pieces. But since I had just signed up to, I just signed my soul to the physics department, I thought I should understand a little better what this scientific life that I had signed up for was. So I made my way to the National Academy of Sciences headquarters, which is in Washington, D.C. So I wandered in past security somehow. I don't know why security let me in, but I found myself basically in the lobby in front of this beautiful painting that had a steampunk style. And I actually have a copy of it right near my desk. It has some instruments like a globe and I think a compass, and there are some equations written around.
If you wouldn't mind holding it up, because it's a very interesting painting. Can you reach it from where you are?
Just about. Can you see that?
Bring it a little bit closer because it's being filtered out.
Let me.
Yes, that's a little better.
Maybe
it's
I
a little
can turn
hard to
off
see
my back.
because of, the background is filtering it. Yeah.
Yes.
That's much better. Yeah.
And it has this beautiful gaze onto the sky outside and the fashion of inspiration and aspirations. So I just fell in love with it. And then a few years later, during my PhD, after I had really committed myself to the scientific life, I emailed the painter, Robert Van Branken, and said, this is painting has really stuck with me ever since I wandered into the National Academy of Sciences headquarters. Do you have any prints that I could buy? And he just sent me some prints. It was very kind of him. And so I keep a copy by my desk. And actually this painting is even more significant to me because it's called Everything at Once or One Thing at a Time. And if anyone here knows anything about quantum physics, then you know that one feature of quantum systems is that they can be in superpositions. For instance, if you have an electron, then in a very loose, hazy sense, it can sort of behave as though it's in multiple places at the same time. But if you measure its position, then your detector will read out only one position. And so I think of superposition as an answer to the question, everything at once or one thing at a time, namely everything at once. And then another very important aspect of quantum physics, namely measurement, is the other answer, just one thing at a time.
That's great. So you start each chapter with a snippet from what sounds like a quantum steampunk novel. Could you maybe tell the audience a little bit about that? What inspired you to incorporate these snippets into your book? Do the names of the characters have any significance other than that they happen to be A, B, C?
Sure. So the book is mostly nonfiction, but there is at the beginning of each chapter this excerpt from an imaginary quantum steampunk novel that lives in my imagination. I tried out this technique in an article that I'd written for Scientific American that was published in 2020 because I thought it would just be fun to play with steampunk motifs in work about serious science. And there is in steampunk a feature that you'll often find in many stories is this very spirited, vivacious young girl who refuses to be defined by the expectations of Victorian society and limited by their corsets. Another feature is the dark and Sherlock Holmesian type streets of Victorian London that are dangerous at night. So I thought it would be fun to put in, sort of play with these steampunk elements in the book, especially since the science quantum steampunk, I think, is fun and really imaginative. Also, yes, there are some characters in this imaginary steampunk novel who are called Audrey, Baxter, Caspian, and Ewart, because in information and quantum information settings, we'll often describe an information processing protocol, like sending information down a wire, in terms of some agents who perform this protocol. And often the agents are called Alice and Bob. For instance, we'll often talk about Alice wanting to send a message to Bob. And sometimes they have a friend, Charlie, who helps them. And if we're talking about a cryptography protocol, then there will be some character Eve who is eavesdropping on them. And I think it's really useful to think in these terms of people who are performing a protocol, and you can analyze the protocol asking, what can these characters achieve? What can these agents achieve if they have just classical resources, or what can these agents achieve if they have quantum resources? And that's how we learn the difference between the classical world and the quantum world. But Alice, Bob, Charlie, and Eve have been used so often that I didn't want to use those names again. So I used the more Victorian versions of Audrey and Baxter and so on.
That's great. So actually, this is a good segue into my next question. You were talking about using these pieces of this imaginary quantum steampunk novel to help your readers understand differences between classical and quantum phenomena. What's the best way, in your mind, for people to think about the difference between quantum computers and ordinary, classical computers, like the kinds that we have on our desks?
One way to think of them is that quantum computers use entanglement. That's very key to quantum computers. Entanglement is this relationship that quantum particles can share. It makes the particles very strongly correlated. Another way to think about what separates classical computers from quantum computers is what one can do well that the other can't do as well. For instance, quantum computers are very good at simulating quantum materials and molecules. So they'll be very useful, and they've started to be useful for research and development into material science and chemistry. There are also certain optimization problems that quantum computers might be more useful for. So some, for instance, companies are trying to see if there are possible applications of things like traffic flow. And there are also some cryptographic protocols, such as one of the most famous cryptographic protocols that we've probably used in our everyday lives is based on how it can be very difficult for a classical computer to find prime number factors of a very, very large number. And so if you name some very, very large number and ask what are the prime factors of that number, it'll take a classical computer a long time to solve this problem. You can imagine growing the size of this number that you're supposed to factor, and the size of the classical computer that you need will grow exponentially. And meanwhile, the size of the quantum computer that you need to solve that problem will grow much more slowly. And so you need fewer quantum resources. The quantum computer is better equipped to handle this problem. So not all problems are well suited to quantum computers. For instance, I don't recommend doing your taxes on quantum computers, but certain problems it can excel at. And these tend to be the problems where the size of the classical computer that you need will grow exponentially in the size of the input, the problem you're trying to solve.
It's become a bit of a cliche when talking with someone who is an expert in quantum technologies to ask, do you ever get a little nervous when you say that, oh, probably we're not going to ever need a quantum computer to do your taxes? You know, that you might be remembered as people many decades ago who used to talk about how the world will only need 5 computers and they'll only be at major universities and ordinary people won't ever need computers. Do you ever worry about that, or do you feel like we're on more solid ground in saying that, you know, quantum computers?
I hope that's the situation. It's at the moment, we don't directly foresee that people will have quantum computers in their homes, but I really hope that it turns out to be the case that the algorithms that we have, the problems that we find that we can solve expand so much that quantum computers do enhance our lives in ways that we don't imagine now. So I think that's a wonderful potential.
Do you have a sense at this point about when quantum computers might become, you know, widespread, genuinely widespread? Are we talking 10 years? Are we talking 50 years, 100 years? Or is it really just not possible to say anything at this point?
It depends on which type of quantum computer we're talking about. There are 2 classes of quantum computers. There are quantum simulators. These are computers that are well suited to solve just problems in a specific class. For instance, they might be able to simulate materials of a certain type. Then there are universal quantum computers, which are reprogrammable. So you can program it to solve one type of problem and then reprogram it to solve a very different type of problem. Quantum simulators exist. They have, I think some of them have thousands of particles in them. We've had them for a number of years, and they've started being useful in helping us observe things like phase transitions that we've never seen before. Some well-known phases from our everyday lives include solid and liquid, but quantum systems can be in much more exotic phases. So quantum simulators have been useful. I've partnered with labs in using them. Then as for universal quantum computers, or let's say reprogrammable quantum computers for the moment, small versions of those exist. They tend to have between 10 and 100 qubits, basic units of quantum information. We're going to need for them to have hundreds of thousands of qubits. So there's quite a ways to go. They're being used at the moment for some small tasks, but they won't, say, solve the factoring problem that I described earlier for any significant numbers. But what we need now is the ability to correct quantum errors in quantum computers on a large scale. That is a really difficult problem. And my understanding is the consensus is in the field feels that is that this will take probably a couple of decades or so.
So you do mention in the book that there are skeptics about quantum computers out there. Why are this relatively small number of people in this field still skeptical about whether quantum computers are realizable?
It's really, really difficult to control quantum systems. In a sense, quantum systems are really easily distracted. For instance, suppose that you have an atom that's entangled with an atom that I'm holding, and we want to use this entanglement as a resource to perform some computation or some communication task. Then we would like to have this controlled entanglement stay there for a little while so we can manipulate it and make use of it. But if anything comes near my atom, any stray dust particles or photons come near my atom will get distracted and start entangling with those. So the entanglement is going to spread all over the place into parts of the environment that I can't control. And it's very difficult to get the atoms in an extremely, or whatever type of physical system we're using to create a quantum computer. It's very difficult to get that into a really clean environment so that the particles aren't distracted and are just going to share their entanglement and maintain their entanglement as they should. But experimentalists have been doing an absolutely amazing job. What they can achieve now, the founders of quantum theory thought would be impossible.
So you describe thermodynamics and quantum computing as both sharing what you describe as an operationalist philosophy. I was hoping you might explain what you mean by that and why it makes a difference.
Yeah, in both theories, we think in terms of agents who are trying to perform tasks. And then we ask, how efficiently can the agents perform these tasks? For instance, in the case of thermodynamics, it's of great interest to a thermodynamicist to describe an engine. Suppose that I have an environment that's hot and an environment that's cold, and an engine that I can use to let heat flow from one environment to the other and extract some of the energy to power a factory. How efficiently can I do that? How much work can I extract? Similarly, when we talk about information theory, we're thinking about, say, an Alice or an Audrey who wants to send information down a channel to Bob or Baxter. And we ask, how many resources does Audrey need in order to do that? If we're asking about the quantum version of the problem, we're asking, suppose that Audrey has a quantum message, and into how few basic units of quantum information can she squeeze that message to send it compactly over to Baxter. But in both cases, we're thinking about agents trying to perform tasks efficiently. And this way of thinking is useful for concretizing or making concrete some ideas that can seem very abstract, such as the notion of uncertainty or entanglement. Entanglement is a really complicated idea. But if you start asking, well, what can I achieve if I have some entanglement? Then you can make the question concrete.
Yeah, so moving this conversation, continuing to move it into a somewhat more conceptual direction, because there are a lot of really amazing concepts that you introduce and talk about in the book, and you do a really remarkably good job clarifying them. I can't recommend enough your book. So quantum thermodynamics in particular makes us rethink many concepts, even basic things like heat and work. You talked a little bit about these things in your introductory slides. In your book, you write about there being a menagerie of different definitions of these things. Could you give us maybe a window into that, into what you meant by that term?
Sure. So as I mentioned when going through my slides, it's difficult to define even the notion of heat in a quantum context, partially because of the uncertainty principle. Well, to start with, I mentioned that quantum systems can be in superpositions. So an atom can be in a superposition of having different energies. And then suppose that it absorbs some heat, and also suppose that you turn on a magnetic field with some control, so you're also performing work on the system. The heat and work are the two types of energy that are transferred in between systems. Then as a thermodynamicist, you would want to measure how much work the atom has absorbed, and also how much heat it has absorbed and how much work has been performed on it. But this atom might not even have had a well-defined energy to begin with, and it might not even have a well-defined energy at the end of this process. So how do we even define its energy in just one trial of this protocol if its energy isn't well defined? And then how do we disentangle the heat from the work? Again, we don't want to measure the atom's energy because measuring the energy will disturb the energy. So all of this seems very up in the air and uncertain. So different quantum thermodynamicists have come up with different definitions of heat and work that go along with different ways of measuring quantum heat and quantum work. For instance, there's most people who encounter quantum measurements encounter the idea of the collapse of the wave function. So suppose that your atom begins in a superposition of many different energies. Then if you measure the energy, then after the measurement, the atom will have a well-defined energy. And we say that its wave function has collapsed. But quantum measurements can actually be more subtle, and you can measure a system just weakly so that you don't actually disturb it very much. Although on the other hand, you don't get a whole lot of information about how much energy it has. So you're not really sure how much energy it has. But if you perform many, many trials, then you can build up statistics to tell you about how much energy it had on average, something like that. So that's one example definition of a system's energy change. You can use weak measurements to define how much heat or work a system absorbs. And so I think of this definition of heat or work in terms of weak measurements as sort of like a hummingbird that lights very softly on your shoulder and doesn't bother you very much. And in the book, I associate the different definitions of quantum heat and work with different species in what I think of as a Victorian menagerie. So actually, every time I find a new definition of quantum heat or work, I store it in a file that I called Menagerie of Quantum Heat and Work. And I think that this makes quantum thermodynamics rich in a sense. In some fields of physics, we try to unify theories and get rid of variation and narrow down ideas. But I think that in the case of quantum thermodynamics, it might make sense to have these many definitions, because how we should think of heat and work might depend on what system we're holding and how we can poke it and how we can measure it.
So, in old-fashioned classical, semi-classical thermodynamics and in quantum thermodynamics, the concept of entropy plays a really important role, and you talk a lot about entropy in the book because it's very hard to talk about thermodynamics without talking about entropy, or information or quantum information without talking about entropy. Entropy is a notoriously difficult concept to explain. How do you explain it? Maybe you could talk a little bit about how you explain it in the book. What entropy is, or maybe more appropriately, given the menagerie of different notions of heat and work and the different notions of entropy, maybe you could say a little bit about what entropies are. Why is it so important? And please tell us, what does it have to do with the human liver or Edgar Allan Poe's poem, The Raven?
So these references point to how in the book I basically provide a window onto my mind and how I think, which is kind of odd. So I'll start with the more straightforward definitions. So what is entropy? Entropy is a measure of uncertainty. For instance, I lived in Cambridge for a few years, and so I can appreciate that the dominant weather pattern on any given day in Cambridge is extremely uncertain. So if you ask about any given day, there's going to be some probability of sun, some probability of snow, some probability of rain, some probability of clouds. And suppose that you learn that today, sun is the dominant weather pattern. Then how surprised are you? How much information do you learn? That's a measure of how uncertain you are. And that can be used to define an entropic quantity. But there are other questions that we can ask, like suppose that this happens on many, many days. On each day, you learn the weather, you're surprised to some extent. Next day, you learn the weather, you're surprised to some extent. How uncertain are you on average across many days? That is measured by another entropy. And it makes sense that there are many different measures of uncertainty because, again, uncertainty is kind of a vague concept. So exactly what we mean by the word depends on exactly what we're trying to do, like predict the weather on one day or predict the weather on average over many days. And in thermodynamics, entropy similarly measures uncertainty. Suppose that we have the thermodynamicist's favorite system, a gas in a box. And suppose that we know that that gas has some energy and some volume and some number of particles. That's all we know. And there's a lot about the gas that we're uncertain about. Where are the particles physically? How are they configured? What speeds are they moving it with? In what directions are they moving? All the possible arrangements of the particles, all these possible configurations, we have no idea which one is correct. And so our uncertainty about that, given that we know just the total energy, total volume, and total particle number, that is a thermodynamic entropy. So there are many different entropies that are relevant to information theory and thermodynamics. And over the past few years, as we've extended thermodynamics to the regime of the small, to quantum thermodynamics, we've learned that different information processing tasks and different energy processing tasks have efficiencies quantified by different entropies. So in the book, I mentioned that I had a wonderful 9th grade biology teacher who said, if you ever don't know the answer to a question on a test of mine, write down liver. Because the liver performs a ridiculous number of functions in the human body. So if you ever don't know the answer to a biology question and you answer liver, you have an anomalously high probability of being correct. Similarly, if someone asks you, what is the best efficiency with which we can perform some information processing task or some thermodynamic task, and you say, oh, it's given by an entropy, then you have an anomalously high probability of being correct. So that's what entropy has to do with livers. And then as for the raven, I mentioned that when we think about processing information or processing energy on small scales, then actually a whole lot more entropies become relevant and measure our efficiencies than in the conventional thermodynamic setting of lots and lots and lots of particles. In conventional thermodynamics, the type of thermodynamics developed during the 1800s, really basically only one entropy is relevant, and it's the entropy that I described when talking about the gas in a box. So when you're doing quantum thermodynamics, you could be thinking about just single particles, but then you could imagine, thinking about larger systems, more particles, more particles, more particles. And eventually, all of these entropies that are relevant collapse onto just this one entropy that is reminiscent of what we used in the thermodynamics of the 1800s. And so that's relevant to the raven because in the book, I could have just said all of these entropies collapse onto one entropy, but it reminded me of a portion of the Raven. Probably most people here know that the Raven is a poem by Edgar Allan Poe. The speaker is a young man whose love, Lenore, has just passed away. And he is trying to distract himself from thinking about her by reading late at night. And he hears a tapping on his door. He thinks, good heavens, oh my goodness, what could that possibly be? And he opens the door and looks into the darkened hallway. And the poem says, deep into that darkness peering, long I stood there, wondering, fearing, doubting, dreaming dreams no mortal ever dared to dream before. But the silence wasn't broken, and the darkness gave no token, and the only word there spoken was the whispered word, Lenore. This I whispered, and an echo murmured back the word, Lenore. Merely this said nothing more. Then into the chamber turning, all my soul within me burning, soon I heard again a tapping somewhat louder than before. Surely, said I, surely that is something at my window lattice. Let me see then what thereat is and this mystery explore. Let my heart be still a moment and this mystery explore. 'Tis the wind and nothing more. Open here I flung the shutter when, with many a flirt and flutter, in there stepped a stately raven of the saintly days of yore. So all his dreams and nightmares and fears and horrors collapsed onto this one raven. And so that is perhaps a little out there way of saying that all of these entropies collapse onto just one entropy from conventional thermodynamics.
Not the least obeisance, maybe not a minute stopped or stady, but with me and of lord or lady, perched above my chamber door, perched upon a bust of chalice above my chamber door, perched and sat, and nothing more.
Exactly.
I did a high school one-act performance of The Raven. Fortunately, long before the ubiquity of cell phone cameras. So, okay.
Here is your moment.
That was my moment. Okay, we're just about out of time, and I want to make sure there's plenty of time for questions. I just want to say there are so many incredibly interesting and important topics discussed in this book. They have amazing names: fluctuation relations and resource theories, one-shot thermodynamics, scrambling, algorithmic cooling, quantum thermometry. If people are interested in any of these amazing sounding things, I highly recommend reading the book. I do have one very last quick question. I just have to ask this. Could you tell our audience about spooky olfaction at a distance?
Sure. So entanglement is often called spooky action at a distance because that's what Einstein called it. Because in this very cartoon picture of how entanglement works, if you have an atom and I have an atom, we entangle them and then we bring them as far apart as we please. If you measure your atom, then in some kind of loose sense, you're instantaneously changing my atom, even though these atoms could be as far apart as we please. So Einstein thought that this was a very bizarre phenomenon and sort of make fun of it. He called it spooky action at a distance. Nowadays, as I mentioned when presenting my slides, quantum technologies and concepts and so on are incredibly popular, not only with governments and with companies, but also in Hollywood, just all over the place. So all sorts of random products are called quantum. There's a quantum dishwashing detergent, and a colleague of mine posted a photo on Facebook of him holding up a deodorant called quantum deodorant. And so I showed it to my husband, who is very big on puns. So he called that spooky olfaction at a distance.
That's great. All right, let's turn to audience questions. We have a whole bunch. Okay, so the first question, and for this, I think if I can ask you to bring your background back, the first question is, I'm loving the image in your background. What is this amazing contraption?
Sure, I'd be happy to explain. So I was contacted a couple of years ago by a steampunk artist, actually not far from Boston. His name is Bruce Rosenbaum, and he creates wonderful, kinetic, interactive steampunk sculptures. He had seen a talk of mine online, and he said, let's collaborate on a quantum steampunk sculpture. So this is our idea for depicting a quantum engine. In the center is the quantum engine formed from a trapped ion controlled by lasers, and the part on the outside is supposed to be the classical analog of that. So I didn't make the drawing. A professional illustrator did, much better than I ever could. And of course, the magic ingredient for any project is funding. So we're looking for funding to turn the drawing into reality.
It's great. So I have another question from the audience, this one particularly close to my heart. Thank you very much for the person who asked this question. You talked a bit about your interdisciplinary interests, not only acknowledging your early educational pursuits, but also just how much this book benefits from your overall sense of aesthetics, vision, and literary knowledge. Do you think all science could use a bit of this imagination?
I'd say I found it very beneficial myself. And I've found very great value to having a liberal arts education in a physics career. I actually wrote a blog post about this. I write for Quantum Frontiers, which is Caltech's the blog of Caltech's Institute for Quantum Information and Matter. And within the past few months, I wrote about how having a liberal arts education has helped me knit together ideas from different disciplines, from thermodynamics and chemistry and information theory and computer science, and just see things in a different way and also pick up on information differently. So I've been very, very grateful to have a liberal arts education as a physicist.
That's great. Another question, this one's a little more technical. In your view, in quantum mechanics, should we think about probability in a frequentist sense or a Bayesian sense, neither or both? Maybe you could say a little bit about what those mean and if you have any opinions on the matter.
Maybe I shouldn't put forth political opinions in public lectures.
It's very controversial, so.
Yes, so when we are, although I should say there are a number of people in quantum information theory who ascribe to Bayesianism. So, and when we use a Bayesian approach, then when we think about an event that might happen at some point, we're not sure exactly how the event will turn out, then we have in mind some model of what the possible probabilities are associated with the possible outcomes. And each time we gain new information, we should update this set of probabilities, this prior distribution. But maybe I shouldn't say too much about politics in a public lecture.
Okay. All right. So this is a somewhat less politically fraught question. It's a bit of a technical question. So we have a question from the audience. I thought that entropy was a measure of organization or disorganization of a system. This is the thinking of entropy from the paradigm of like order, disorder. And you described it in very different terms. I know from experience teaching that, often students come with this order, disorder way of thinking about entropy, and then we have to explain it's more subtle than that. So how would you finesse that? How would you explain the distinction and how would you relate these two ways of thinking about entropy?
If a system is disordered, there are a lot more ways that it can be disordered. One common example that's in some science writing is, think of a kid's bedroom. There are so many ways that it can be messy. The blanket can be totally off the bed, or it can be scrunched up in the middle of the bed, and so on and so forth. Whereas there are relatively few ways for the bedroom to be ordered. And so imagine or think of all the possible ways that the room can be disordered. That's sort of like the entropy of the system. So I described entropy in terms of what we don't know about a system. And to connect these two ideas, let's go back to the story that I told earlier about a gas in a box. Suppose that all of the gas molecules are clumped up together in one corner of the box. And this is a fairly orderly system. It's as though all of the clothes in the bedroom are tucked into the drawers rather than being anywhere all across the room. And if you think about the gas molecules clumped together in a corner of the box in this kind of well-ordered state, then you'll find there aren't quite so many configurations that the gas can be in, because a molecule could be in the gas, could be here or here or here or here or here, but it can't be all the way on the opposite side of the box. So this gas that's all clumped up in a corner of the box that we said is kind of like an ordered system also has a low entropy. So that's how we can connect the two ideas. It might be sort of quicker if you have only a sentence or two available to describe entropy, then it might be easier to describe it as a measure of disorder. But I often feel like a more precise definition is in terms of what we don't know about the system.
So this is another really good question. When you think about quantum computers, we have sort of a cartoon picture of a quantum computer, but like in the real world, if you had a quantum computer in front of you, what kind of user interface does it have? Does it have a quantum keyboard? Does it have a quantum mouse? And as you mentioned that there are some, that there exist some actual physical implementations of quantum computers today. You know, how do people interact with them? What does the interface look like?
You can interact today with quantum computers via the internet. There are a number of companies that make small versions of quantum computers available online, such as IBM. Also, Amazon Web Services provides access to quantum computers by a few companies. I think IonQ, which I mentioned earlier, and Rigetti, and maybe another. There's a lot of work that's been done to make quantum computers usable to a wide range of people. And there's a lot of ongoing work that involves developing software for quantum computers to bridge the quantum to the classical user. So I encourage everyone who's interested in this question to go out and explore the quantum computers that you can use today.
That's great. So my clock shows that we're just at the hour. I want to be respectful of the time of everyone in our audience and also your time. So I think we should stop there. But I wanted to thank you so much. This was an incredibly informative and enriching conversation. Thank you for taking the time to answer my questions and questions from our audience. I highly recommend people go out and buy this book. It's really amazing and you'll learn a lot. And what I think is amazing about it is, although you describe a tremendous amount about the science, you talk a lot about technology, some of which exist, there are a couple of places in the book where you say, only a few places, but a couple of places where you say, stay tuned for the next edition, because this is all cutting edge science and your next edition, this is a scientific revolution that's happening in real time. It's really very exciting. And if people want to get a sense of it, I highly recommend they get the book. So thank you so much for your time. And thanks to the Harvard Bookstore for inviting us.
Yeah, thanks very much for the conversation and also for the input from the audience. This has been a lot of fun.
And thank you both for this fantastic presentation and conversation. It's been so lovely to see the aesthetic value. It's been so lovely to hear you both talk so wonderfully. And as well as your recitation of The Raven was phenomenal. I was losing it. Thank you so much.
I feel like we should partner on a longer version for Poetry Month or something.
Yeah.
My wife is rolling her eyes so much now, I can't even.
Well, we all found it delightful. But so thanks again for joining us. Thanks to all of you out there for spending part of your evening with us. Please learn more about this book and purchase your copy of Quantum Steampunk at harvard.com. I put the link in the chat a couple times. On behalf of Harvard Bookstore, the Harvard Division of Science, and the Harvard Library, all here in Cambridge, Massachusetts, have a good night, keep reading, and be well. Thanks again, everyone.
Thanks so much. It's been a pleasure.
Thanks again.